Okay, we want to talk about the direction of a torque and use that as a motivation to complete the definition of torque. If we have the r vector and the f vector, and I haven't bothered drawing the object, if we have the r vector and the f vector, remember that the torque is going to be the product of the f perpendicular with the r vector, the magnitude of the torque. So here we have f perpendicular, f parallel, f is gone. So the torque equals rf. Magnitude of the torque equals magnitude of r times f. Doesn't tell us what the direction of the torque is. Now we can see what the direction of this torque ought to be. It's going to be counterclockwise, or at least it's going to have an influence of rotating counterclockwise, but what we would really like is, I'm sorry, that one's clockwise. Obviously clock goes this way. I know that. Okay. If we want a single direction for the torque, though, this isn't a single direction. This is a number of directions. You can't draw an arrow in the direction of the torque here. So here the torque is clockwise. So that tells us in what sense the torque rotates, but what single vector could distinguish clockwise from counterclockwise? There's no single vector in the plane that indicates clockwise direction. Well, let me demonstrate with a strap. Okay, if this strap is rotating, let's say it's rotating, I'll put it up here, rotate it in this plane. Okay, there's no vector in the plane that tells you the direction in which this is rotating. It would distinguish this motion from this motion. The only way to distinguish the motion, and I'm going to move the thing over here a little bit, is with a vector perpendicular to the plane. And if we're going to use a vector perpendicular to the plane to indicate the direction of rotation, then it makes a certain amount of sense to use the cross product of these two vectors. Okay, so a vector perpendicular to the plane can distinguish clockwise from counterclockwise in the plane. That's because we have two possible vectors. If this thing's rotating in this plane, we could have a vector in this direction or a vector in this direction. One of those vectors could indicate clockwise motion, another could indicate counterclockwise motion. So as I said a minute ago, the cross product of these vectors is in the plane perpendicular to the rotation. And the cross product of r, say with f, in this case, by the right-hand rule, the rotation we have here, in the direction of r, turn it towards the direction of f, the thumb goes into the board. So that the clockwise rotation could be represented by a vector into the board, a counterclockwise rotation, a vector out of the board. Okay, well, with that motivation, we describe the torque as the cross product of the r vector and the f vector. The magnitude of the torque then equals r times, no, magnitude of r, I'll be explicit about these magnitudes, magnitude of f times the sine of theta, where theta is the angle between them, the familiar definition of a cross product, and direction by the right-hand rule. Now that's equivalent to saying that it's r times the f perpendicular, the cross product of r with f perpendicular, because note that magnitude of f sine theta is I guess I need to put a magnitude around the sine theta, is the magnitude of f perpendicular. That's fairly obvious. Theta being the angle between the r vector and the f vector. Theta would be this angle here, and the sine of that angle multiplied by the f vector gives you the f perpendicular. Cosine, of course, gives you the f parallel. So we have a definition of torque that's motivated by the definition of work, the fact that the change, that the work done on an interval is a change in kinetic energy on that interval, and we've moved that into the definition of torque as a cross product of the r and the f. Now it should be clear from this that we can write tau equals rf sine theta, where all these are magnitudes and there's no indication of direction. The direction comes from doing the cross product, but we'll just talk about the magnitude for a moment. This equation can be written two different ways, and in two additional ways. We can group the f with the sine theta, so we have r times f sine theta, which is just r times f perpendicular, and that's what we're looking at here. Or we could group the sine theta with the r, so f equals, the torque equals f times the quantity r sine theta, which we just call f times L, where L equals r sine theta. And there's an interpretation of this. That's a very significant and useful interpretation. So let's go to the case again where we have the r vector and the f vector. Could be any object. The f vector has a line of action, which is just a line through the point of application in the direction of f. So we have the line of action. Line of action of the force. The L quantity is just the distance from the axis to the line of action. So what's that distance? Well, that distance is the projection of the projection of what? Well, here we have a perpendicular. Here we have then L. Okay? And that's just the projection of the r vector on the f vector. You might have detected a little uncertainty in my voice, and I was looking at this to make sure I said that right, and I found that I didn't. The projection of the r vector on the f vector would be here. So there's the projection of the r vector and the f vector. We subtract that projection from the r vector. So be the magnitude of r minus the projection of the r vector and the f vector. In any case, you can see from the figure where that length L is, and if this is the angle between the f vector and the r vector, that's equal to this angle here, and just looking at the right triangle, that's going to be, L is going to be r times the sine of this angle. L is opposite to the angle, r is the hypotenuse, etc. So you can work that out very easily. In any case, the main thing is this picture of the line of action of the force and its closest approach to the axis, because that's where the L vector will be, this L segment is perpendicular at the point of closest approach. Okay, very important and useful, as we'll see in analyzing some problems. This L here is called the lever arm, and if we want to make a vector out of it, then we could have the L vector and leave it to you to verify that the torque is the lever arm or moment arm crossed with the F vector. It's very straightforward that the cross product of this with F is the same as the cross product of this with F. Of course, I'm using my left hand. My right hand's a little clumsy to get up there, but you understand I'm indicating we're going to use the right hand rule to do this, even if I'm using my left hand. Okay, so that's called the lever arm. It's also called the moment arm. And we can express it as a vector or as a scalar. But if we're going to do the vector calculation, we would want to express it as a vector so we could do the cross product.